Title: Why Modern Fighter Jets Are Built to Be Unstable. Intro hook: The airplane that should have crashed. In 1973, during early testing of the General Dynamics F-16 Fighting Falcon, something strange happened. The aircraft didn't want to fly straight. It didn't naturally return to level flight when disturbed. It didn't self-correct like conventional aircraft. In fact, if you let go of the controls, it would diverge. By classical aeronautical standards, this aircraft was unstable. And instability, in aviation, usually ends in wreckage. Visual: archival footage of early F-16 test flights, overlay of stability graph diverging over time. For decades, aircraft designers had one sacred rule: make the airplane stable, make it forgiving, make it want to fly straight. So why would engineers deliberately violate the most fundamental safety principle of flight? Because physics forced them to. Modern air combat demands maneuverability beyond what stable aerodynamics can provide. To win dogfights, evade missiles, and control supersonic shockwaves, fighter jets had to break a rule and then invent entirely new control systems to survive the consequences. Today, we're going to unpack why stable aircraft are limited, the physics of aerodynamic stability, why instability creates maneuverability, how computers made unstable aircraft flyable, and the enormous trade-offs behind this decision. This isn't about recklessness. It's about engineering pushed to the edge of physics. 1. The context: why stability became a problem. Airplanes are naturally designed to behave like darts. Throw a dart. It stabilizes itself because the center of pressure sits behind the center of mass. That creates a restoring moment. Visual: diagram of dart with center of mass, CG, and center of pressure, CP. Early aircraft like the Supermarine Spitfire followed the same principle. The wing and tail arrangement ensured. If the nose pitched up, aerodynamic forces pushed it back down. If it pitched down, lift pulled it back up. This is called static longitudinal stability. Mathematically, it means dm/d alpha 0, where m equals pitching moment, alpha equals angle of attack, negative slope equals restoring force. Stable aircraft are easy to fly. They are forgiving. They are safe. But they are not agile. And after Vietnam, agility became everything. The Vietnam wake-up call. In the 1960s, American fighters like the McDonnell Douglas F-4 Phantom II relied heavily on speed and missiles. The assumption was simple: dogfights were obsolete. That assumption was wrong. Engagements frequently devolved into close-range maneuvering. And maneuvering is governed by one thing: energy management. 2. The physics constraint: stability versus maneuverability. Let's reduce this to first principles. An aircraft in flight must satisfy. Lift equals weight. Thrust equals drag. But maneuvering introduces a new variable: load factor, N. N equals lift/weight. To turn tightly, you need high load factor, which requires high lift, which requires high angle of attack. Here's the problem. In a stable aircraft, when you increase angle of attack, the tail produces a downward force to stabilize it. That downward force reduces total lift, meaning you are fighting your own airplane. Visual: stable aircraft diagram showing tail pushing down. A stable aircraft resists pitching up. It wants to return to equilibrium. An unstable aircraft does not. And that changes everything. 3. The hero moment: relaxed static stability. Engineers realized something radical. If we move the center of gravity slightly aft, closer to the aerodynamic center, we can reduce the restoring force. Push it far enough back, and the aircraft becomes unstable. This is called relaxed static stability, RSS. Visual: CG shifting aft relative to neutral point. Instead of dm/d alpha being strongly negative, it becomes near zero, or slightly positive. Now the aircraft wants to pitch up instead of resist it. That means faster pitch response, higher instantaneous turn rate, a less trim drag, better energy retention. In combat, milliseconds matter. RSS reduces control force requirements dramatically, but it also means, without correction, the aircraft diverges rapidly, fatally. 4. Enter the computer, fly-by-wire. Before the 1970s, this design was impossible. Human reaction time: 200 milliseconds. An unstable aircraft can diverge in less than that. The solution? Digital fly-by-wire, FBW. The General Dynamics F 16 Fighting Falcon became the first production fighter designed from the start to be aerodynamically unstable and controlled entirely by computers. Visual block diagram of fly-by-wire system. Pilot input, computer control surfaces. The computer makes thousands of corrections per second. It artificially creates stability. In effect, the aircraft is unstable. The software makes it behave stable until the pilot demands aggression. This separation between airframe physics and pilot command changed fighter design forever. 5. The trade-off FS. You don't get something for nothing. Unstable aircraft are not universally better. They come with serious costs. 1. Complexity. FBW systems require redundant computers, triple or quadruple fail-safe architectures, independent power systems. Visual, quad-redundant flight computer architecture diagram. This increases cost and maintenance burden. 2. Certification risk. A stable aircraft can glide. An unstable one cannot. If computers fail, the aircraft is uncontrollable. This is why commercial airliners like the Boeing 777 retain positive static stability. Airliners prioritize predictability over agility. 3. Training. Unstable fighters allow extreme maneuvers, but pilots must manage energy carefully. High angle of attack maneuvers bleed speed rapidly. Energy lost equals vulnerability. 6. Super maneuverability, beyond instability. Aircraft like the Sukhoi Su-35 and Lockheed Martin F-22 Raptor combine instability with thrust vectoring. Visual, 3D thrust vectoring nozzle diagram. This allows control even when airflow separates. Boundary layer separation normally leads to stall, but vectored thrust provides control moments independent of airflow. This is post-stall maneuvering. However, post-stall equals massive energy loss. It looks dramatic, but tactically, it's situational. Again, trade-offs. 7. Stealth and instability. Modern fighters like the Lockheed Martin F-35 Lightning II also integrate stealth shaping. Stealth geometry often compromises natural aerodynamic stability. Diamond-shaped fuselages, canted tails, blended bodies. These shift aerodynamic centers. Instability becomes a byproduct of stealth optimization, so the computer isn't optional. It's mandatory. 8. Why not make it stable and just add bigger engines? Because maneuverability isn't about brute force. It's about moment arm leverage. Pitching moment. M equals lift times distance. If you want rapid nose authority, you need favorable geometry. Stability adds counteracting moments. Instability removes them. Engines add thrust. They do not remove aerodynamic resistance to pitching. Different physics domains. 9. Economic reality. Modern fighters cost. F-35, $80 million per unit. F-22, $150 plus million program average. Much of that cost lies in flight computers, control software, redundant systems, integration testing. Unstable design demands software validation at extreme edge cases. Testing complexity increases exponentially. Instability is cheap aerodynamically, but expensive digitally. 10. The verdict. Are unstable fighters viable for the future? Yes, for military aviation, because air combat rewards agility, energy control, reduced trim drag, stealth integration. But for civilian aviation? No. Passenger jets prioritize predictability, fuel economy, passive safety. Instability only makes sense when combat demands it. Final thought, human ingenuity versus physics. Nature prefers equilibrium. Stable systems survive. Engineers, however, wanted performance beyond equilibrium. So they built machines that violate natural stability, and then created artificial stability through computation. Modern fighter jets are not just aircraft. They are unstable systems kept alive by silicon. It's a reminder that engineering progress doesn't eliminate physics. It negotiates with it. And sometimes, winning requires building something that shouldn't fly, and then teaching it how.